Today's objectives are to learn about nuclear fusion and determine whether or not it might be the energy of the future. So the sun, basically, every second, it really converts hydrogen to helium in a process called nuclear fusion. And it generates a massive amount of energy, which is then radiated out in all directions. So what exactly is nuclear fusion? Well, it's really the process of joining together multiple nuclei to form a heavier nucleus. And it's accompanied by the release of a tremendous amount of energy. So let's take a look at what that actually means for inside the sun. So here we have two nuclei. We have the deuterium nuclei, which is basically a heavy hydrogen. Hydrogen normally has one proton and no neutrons. So deuterium is a hydrogen atom that has a proton and one neutron. And so it's actually an isotope of hydrogen. And so normal hydrogen just has one proton, no neutron. Deuterium has one proton, one neutron. And tritium is an even more rare form of hydrogen. It's a hydrogen isotope that happens to have one proton and two neutrons. And if you combine deuterium and tritium under high pressure and or high temperature, you can actually fuse them into helium. And helium will have two protons and two neutrons, and the reaction will generate lots and lots of energy and a neutron that is then expelled from the reaction. So how exactly does this generate energy? Well, we've all heard are familiar with the equation E equals mc squared from Einstein. And basically it says that energy is equal to mass times the speed of light, which is c squared. And the process of nuclear fusion, if you took 1 kilogram of hydrogen and fused it into helium, the resulting mass would only be 0.993 kilograms of helium. And so what that means is that the amount of mass that has been converted to energy is 0.007 kilograms. And so that's your mass. And then c, of course, is the speed of light, which is 3 times 10 to the 8th meters per second. You square that, and ultimately what you get is an energy release of 6.3 times 10 to the 14th joules from 1 kilogram of hydrogen, making this particular type of energy creation probably the most efficient in the universe in terms of the amount of fuel consumed versus the amount of energy that's released. So how is it possible to create fusion on Earth? The sun does it through massive temperatures and incredible pressures. It can actually literally squeeze the nuclei together. But that's difficult to achieve on Earth because we don't have the mass of the sun helping us to compress these nuclei. So we have to come up with clever ways that we can actually do that. And in order to understand this process, we have to talk about the concepts of ignition, density, confinement, and magnetic confinement. The other thing we have to become familiar with is plasma. So plasma happens to be the most common state of matter in the universe, but it really only makes up about 99% of all the observable matter in the universe. And inside a deuterium-tritium fusion reactor, we're basically creating a plasma. So let's go back and circle back to what exactly plasma is. So we have a solid which has molecules that are arranged in a lattice structure, and they have a strong attraction to one another, and makes them very basically solid. And if you heat up that solid, you can melt it and convert it to a liquid, where there still is some molecular attraction between the molecules, and that's what gives us our surface tension, but the molecules are much more free to move about. If you continue to add energy to that liquid, you can convert it to a gas, and now the molecules are rapidly moving about, bumping into one another, and there still are some intermolecular forces. If you keep heating a gas, eventually you can create a plasma, which basically has your nuclei, and all of the electrons are stripped off of the nuclei, giving it a very different type of behavior without those electrons being tied to the individual nuclei. So how can we possibly achieve this on Earth? Well, in order to do this, we have to do three things all at once. We have to have an extremely high temperature. Normally, if we had the pressure from the sun, we could achieve fusion at a much lower temperature. But because we don't have the pressure from the sun, we have to go to extremely high temperatures on the order of several million degrees. The next thing we have to do, after we've created the plasma with these high temperatures, we have to actually confine it in a volume in some way, which is really challenging, because how can you possibly contain something that is 1,000,000 degrees? Because if it touches anything, it'll just melt it. So you have to be clever about that. And then the next thing you have to do is you have to prevent it from losing heat, so that you can use all of that energy in order to create electricity or do something useful with the energy that's actually released. So in order to do all of this, we really have to understand the plasma physics. So we're not using very high densities inside the facilities that we're trying to achieve nuclear fusion in. And so what we have to focus in on is confinement. And basically, we have to keep the heat losses to a minimum. We have to keep all of that energy inside the system by insulating that system and keeping the plasma from actually touching anything in the process. And that has proved to be exceptionally challenging. Stars, like our sun, do it really easily from gravitational confinement. But here on Earth, we've come up with two clever ways to try and contain that plasma, which is at 1,000,000 degrees or more. One is to use magnets to confine the plasma so that it basically stays within a volume but doesn't actually touch any of the surroundings or any of the walls of the chamber. And the second is called inertial confinement, where you actually use up to 200 lasers pointing at a pellet of deuterium and tritium, and the pressure from the lasers can actually confine the plasma to a very small volume. So for these fusion techniques, the most efficient way that scientists have actually come up with to confine a plasma is actually using what's called a tokamak. It is a toroidal magnetic field shown on the right here, where you have these very strong magnets that are able to create a magnetic field that essentially creates a donut-shaped inertial confinement vessel. It creates extremely hot deuterium tritium plasma and confines it within that magnetic field, and you have to maintain that magnetic field because the plasma will vaporize anything it touches, including the walls and the magnets and anything else that it would touch. The second way is that inertial confinement, where you take that small pellet of fuel, the deuterium tritium, and you blast it with these powerful lasers, and those lasers create a massive pressure inside the very small cavity. So where is this actually being achieved? So the biggest tokamak is actually under construction, and it's going to be called the International Thermonuclear Experimental Reactor, ITER, and it's actually located in France, and it's being funded by an international consortium of countries, including the United States. It's a multi-billion-dollar facility. It's the largest of its kind, and they're hoping to have it online by 2025. There have been many smaller tokamak facilities that have shown that the technique is pretty promising. In the United States, we have an inertial confinement system called the National Ignition Facility, and it happens to be located at Lawrence Livermore National Laboratory in Livermore, California, in the United States. This facility has been used primarily for research, but we'll see in a minute it's had a major breakthrough just in the last year. So why is this so hard? Well, it needs temperatures of more than 1,000,000 degrees. The other problem is that tritium, one of the components necessary to generate fusion, is actually unstable. And it decays with a half-life of 12 years, which is pretty quick. So you can't just go to a mine and mine tritium out of the ground. You actually have to make it. There are some theories that there's a significant amount of tritium on the moon, and that if you could go to the moon and mine the tritium there and bring it back, that it would generate, would simplify things quite a bit, but that is yet to be proven. And then the other problem with this, remember that free neutron that that left the reaction? That free neutron is actually potentially dangerous because it's exiting at a high energy, which is a high velocity. And if it strikes the outer part of your containment vessel at that high velocity, it can actually produce radioactive nuclei. And although nuclear fusion doesn't generate any radioactive waste, that neutron interacting with matter can produce radioactive waste associated with the facility itself. So we have to figure out a way to deal with that. So in conclusion, this is just a quick introduction to fusion, but fusion is a promising future energy source. And that breakthrough that I talked about, the National Ignition Facility, achieved break-even in 2023, which means that it actually produced more energy than was required to initiate the reaction and confine it. But it only produced a net energy of about 1.5 megajoules, which is about enough energy to boil like 10 pots of coffee. And it did it for less than 1 second. So clearly that is miles and miles and miles to go before you have a commercially viable energy source that could actually power an electrical grid. But this break-even was a major scientific accomplishment that some people had predicted would not be achieved for another 20 years or so. So the ITER facility has a stated goal of producing 10 times more energy for up to 8 minutes, which will be the next step in trying to move towards continuous nuclear fusion as part of our energy production schemes. But there are still these issues. We still have to figure out what to do with how to come up with tritium. We can generate it, but that takes energy. And we still need to figure out what to do with those free neutrons that are floating about. But there has been one really kind of clever idea that is lining the tokamak with lithium. So lithium is a metal. It's a relatively light metal. It's primarily used in batteries right now. But some scientists have discovered that this lithium-6 isotope is able to capture a neutron. And when it does that, it converts into helium and hydrogen. And you'll notice that hydrogen-3, helium-4 is the standard form of helium with 2 neutrons and 2 protons. But that helium-3 isotope is actually tritium. So in this case, if you can line the tokamak with lithium, you can remove those neutrons and regenerate tritium, and at the same time prevent the buildup of high-level radioactive waste that would have to be dealt with. And because this has been shown to be possible, these lithium blankets are currently a focus of research and will most likely be introduced into the next generation tokamaks. So I'm hopeful that we will continue to invest in research and development so that we can continue making breakthroughs on this very promising future energy source. And once we get nuclear fusion commercialized and able to energize our electrical grid, we have almost limitless amount of energy that will not generate carbon dioxide, will reduce our reliance upon fossil fuels, and will allow for the development of societies across the world, because the access to energy will no longer be an issue. So I'd love to see if this will happen in my lifetime. I don't expect it to, but it is, I think, the future energy source for the Earth.